we'll have, okay, the quick recap of the previous session first, and then we'll proceed to the next session. So in the last class, we did equality checking protocol. Like we checked that if suppose A is sending some file to the B and they are not sending the whole file, A is not sending the whole file. It is only sending it is a type of compressing the file. I'll say not actually the compression protocol, but it's like they are only sending like we did that A is there, then we are turning this into decimal number, and then we are picking up the prime number, computing the residue of that, and then sending that prime and residual number. Then we saw the error also, which can be induced even though we have the same residues, still there can be an error. Then we came up with the Poisson random variable. We saw that in some places it is a special case of binomial also, and in some places where we use Poisson and where we use binomial. Do you remember that, when we use Poisson and when we use binomial?
Ma'am, probability is tending to 0 and n is tending to infinity. Ma'am, we use Poisson.
Yes.
And ma'am, in normal cases we use binomial.
Yes, yes. When n is very large and probability is very small, as I gave the example, like suppose we have to check how many words are misspelled in the huge book. So obviously n is very large and p is very small there in that case. And then we saw about this. Then okay, then we saw the examples there. Then we came up with the concentration inequality, that is Markov inequality, continuous and discrete case, and we saw one or two examples in that also. And then Chebyshev inequality. And when we use Chebyshev and when we use Markov, any idea? Okay, let's glance through the formula and then see. This is Markov inequality, that the probability that x, how like this random variable x is far away from A, then it is bounded by the expectation of x over A, that constant as well as the mean. Okay, let's see now the Chebyshev inequality. How much x is far away from its expected x? It is bounded by the variance here is less than that constant. So any idea when we use Chebyshev and when we use Markov? Can I say in Chebyshev both variance and expectation should be given to us? And
Yes,
in Markov only expectation is required.
Yes, ma'am.
Now, coming to weak linearity of expectation. So we here did two-wise independent random variable. We know this variance of xi. This one we have done already, the formula and everything, the proof as well. Then we proved this. Then weak law of large numbers. Weak law of large numbers we did. Okay, today we'll start from this only. Weak law of large numbers only.
Ma'am, I think we have completed weak law of large numbers.
Okay. So okay, let's start with Chernoff inequality. So you got the idea behind weak law of large numbers. I'll just write it.
Yes,
When
ma'am.
we use so I gave you the example also, like suppose when we do the simulation part, we run our experiment again and again because randomness is induced in it. Suppose I'll get one output at one side and the other output at the other end. Like when I'll run for the first time, I'll get a first output. When I'll run for the second time, the output will change. Maybe there can be various factors of the randomness. One of the factor can be noise. The other factor is suppose I'm communicating something, bandwidth is changing. So there can be a randomness which can be induced in my experiment. So due to that randomness, we run the experiment again and again. And why we run it again and again? So that our sample mean should be approximately equal to the population mean, or I can say the mean, the expectation should be equal to the actual true mean. The uh, the statistic, like whatever we are doing in the simulation, we'll calculate the mean of them. Suppose I got this output 1, output 2, output 3. I ran it for 1,000 times. Then I calculated the mean of them. Whatever is, it should be approximately equal to the true mean. We usually call it as the sample mean should reach the population mean. This is the main gist of it. We call it as ensemble average when we do the simulation part. I'll do the run 1, run 2 till run 1,000, suppose, and I'll take the mean. This is basically ensemble average, and take the mean of the output, and we'll say that it is actually the actual average, actual mean basically. Now coming to Chernoff inequality. Let x be binary random variable with probability of x is equal to 1 is equal to p. Let x1, x2 till let xn be identical to x and mutually independent. Can you tell me what is mutually independent? And we did in weak law of large numbers as two-wise independent, pairwise, or two-wise independent. So what is the difference between mutually independent and this two-wise independent?
Ma'am, mutually independent is much stronger than ma'am two-wise or k-wise, ma'am, because ma'am, it tells that any two subsets of ma'am can be independent to each other, like two or three or even more.
Yes. So any of them can be independent to each other. It need not be only two pairwise independence, I can say. Then sum is equal to summation of xi. Then probability of s is less than 1 minus delta expectation of s. So in previous inequalities or concentration bounds, we saw that how the expectation is far away from the actual, the sum and other things we saw here. But there it was not exponential decay, I can say. Here what they are saying is sum is significantly smaller than the expectation, because we are saying this is strongest inequality, I can say, because the decay here is exponential in nature. So let us prove first this Chernoff inequality, that how the sum is less than the expectation by, and it is bounded by the exponential decay. So let us say mu is equal to expectation of s. What is s here? Sum.
Ma'am, sum of all.
So I can say, and we have also written that they are identical. So I can write, suppose, and let it be p, basically expectation of x. So I have to find this. Expectation of S is less than 1 minus delta expectation of S. Probability of S is less than. So, in place of expectation of S, I have written mu here. Only this. Now, suppose I take exponential on both of the sides, left hand side also, as well as right hand side also. We take, as well as we multiply by minus t. So what should be the inequality sign? Left or right? Like, which is greater?
Greater left one.
Can I say this? So basically, the signs are changed when I'm taking the exponential and multiplying by minus t with this s and 1 minus delta mu. So where t is greater than 0, it's a parameter, I can say, and e, it's the natural log, I can say. Now let's go to Markov inequality. What is Markov inequality? Probability of x is greater than a is less than expectation of x over a. This is Markov inequality. We have studied this. Am I correct?
Yes, ma'am.
So now can I write like this by substituting the values? Expectation of x divided by a. Is it correct?
Yes, ma'am.
Now there is a property that e raised to power a into e raised to power b. I can write it as e raised to power a plus e raised to power b. Which means, suppose I'm writing it as what is S? S is basically the sum of xi's. We know that S is the sum of xi's. S is equal to summation of xi. Now what I'm writing as, can you relate this and tell what I'm doing here?
Yes, ma'am. Ma'am, summation
Can
series
you
is
tell?
converted into multiplication series, ma'am, due to properties of powers.
So I was having a plus b, means this sum was x1 plus x2. So what we are doing is we are converting it to e. We can write it as e raised to power a into e raised to power b. That we know that e power x plus y, the simple formula, I can say. So that is what we have written here. And we know that x are identical in nature. So again, I can write it as I have n number of. Clear?
Yes, ma'am.
Now t of x. Now these are basically Bernoulli trials. What is the expectation formula? Right, and then we'll go through it. Can you explain me Bernoulli trial and then this formula? Can some one of you explain this?
Ma'am, ma'am, Bernoulli, in Bernoulli trials, ma'am, there are only two possibilities. It will happen or either it will not. Ma'am,
Hmm.
probability of happening is p. That's why p into e raised to minus t into 1, and it is added with 1 minus p, that is probability of not happening, and times e to the raise t into 0, that is 1. That's why trying it.
So basically, absolutely correct that Bernoulli trials either 0 or 1, either it will be successful or either it will not be successful. P and 1 minus P and substituting 1 and minus 1. So now write it as 1 minus P plus P e raised to minus T power n 1 minus P common 1 minus e raised to minus T power n. Only I haven't done anything, only I have taken P as common here. Okay, now I'll tell you how we came up with this. We have the other property, though I'm not giving the proof here again. If you want, then we can study about the proof next time. 1 minus epsilon is less than equal to e raised to minus epsilon, which means 1 minus, let us say this is an epsilon, 1 minus epsilon is less than e raised to minus epsilon. It is in this power, which means this will come to e raised to power p 1 minus e raised to minus t. Is it clear?
Yes, ma'am.
We have this formula. We just substituted this till this. This actually comes through this Taylor's theorem we have already done. Okay, I'll tell you. The Maclaurin or Taylor, I can say 1 plus x square by 2. We know that what is the expansion of exponential x cubed by 3 factorial, sorry. Or I can say that e raised to minus epsilon, if we have, then 1 minus epsilon plus epsilon square by 2 plus minus epsilon cube by 3 factorial. So basically they mean that the factorial, basically these positive terms overweighs or outweighs the negative terms. So that is why this is basically greater than 1 minus epsilon. Though I'm not going into deep, this is just intuition behind this formula. This is the expansion. What we are saying is 1 minus epsilon is less than e raised to minus epsilon. How we are saying is that these positive terms are 4 factorial, because of factorial and all of these, they overweighs this negative terms. Basically, like I am saying that epsilon square by 2 factorial, epsilon square by 4 factorial, by 6 factorial, they are overweighing the negative terms because of this factorial terms and all of those. That is basically the intuition behind why this formula came. Should we proceed forward?
Yes, ma'am.
One more thing, if you want, are you noting down side by side, or you want the notes as well? If you want the notes, next time I'm uploading on Drive anyway. I'll share the Drive link with you guys.
Yes, ma'am.
So I'm substituting this value. Suppose let us take it as 1 here and substitute these values here. I mean to say e raised to power expectation of e raised to minus ts. That is what we have calculated. What we have done nothing, just I have substitute this value, and then by Bernoulli trial, as you said that this is this 1 minus p, we got this, and then we have upper bounded by exponential term. So I can basically substitute this value. So can I write in place of expectation of e raised to minus ts this value? because this is greater than this, then obviously expectation of e raised to power minus ts is greater than this term, I can say. Is it correct to
Yes,
write
ma'am.
in this place this value? Yes. So substituting in 1, I can say probability of S less than 1 minus delta mu is less than equal to what we have got here, e raised to power minus np. Np I can write it as u also, mu also, u or mu, whatever we are taking. 1 minus e raised to power minus t. And what was the other term? E raised to power minus t, 1 minus delta mu. Is it clear, or I should tell what we have done? Clear?
Ma'am, where's that ma'am P term? Ma'am, probability term.
Okay. N into P, we are saying that it is equal to the expectation. Mu basically.
Oh, yes, ma'am. Yes. Okay.
So that is why we have written N into P, mu basically. Am I correct?
Yes, ma'am.
So that is why we came up with this formula. And this is basically, if we are dividing, I can say subtracting here. And here it was minus, so plus here. Now, suppose I have to take the I have to, what we have to do is we have to minimize this upper bound, that it shouldn't be greater than this value. I have to minimize this. So for the minimization, what we usually do, we take the derivative and we do the differentiation to minimize it and equate it to 0. That is what we usually do. So let's do that. Right, like this as well. Are they same? Can you check?
Yes, ma'am.
So minus t, uh, wait a second,
Minus.
plus t, है ना?
Yes, ma'am.
So e raised to, so e raised to power t, 1 minus delta, and plus e raised to power minus, plus e raised to power minus t minus 1, because u was minus, and here u, mu or u. Is it fine? Now I have to minimize it. So I take the derivative of this with respect to t. Can you tell me what will be the derivative with respect to t?
Ma'am, 1 minus del minus e raised to minus t.
Yes. Let us take t is equal to log 1 over 1 minus delta. Let us substitute the value of t, 1 log 1 over 1 minus delta. So from where we have given? From here. Now can you tell me how we came up with this? This is given in the class only, like here we came up with this term. Can you tell me how we came up with this term? I want that we should go in depth, not like just whatever is taught in the class, so that we should learn behind the lines how we are coming from one step to the other step. So how we came up with this? Can you tell? Let's try log, substitute log 1 minus delta, the value of t. Is it tough?
No, ma'am.
Actually, I was also confused when I was solving it. Yes, come on. Can I say t 1 minus delta is equal to log 1 over 1 minus delta 1 minus delta? Is it correct?
Yes, ma'am. Can you repeat, please?
I'll not start with this. I'll start with this. What is e raised to minus t? E raised to a minus log 1 over 1 minus delta. If I am substituting log 1 over 1 minus delta
1
as
minus
t.
delta. Yes, ma'am. 1 minus
So
delta.
1 minus delta. So, or I can, if I want to further explain, I'll say that log 1 over 1 minus delta, and as you said, yes, they'll be cancelled out, and I'll get it as 1 minus delta. Absolutely correct. So I have the value of e raised to minus t as 1 minus delta. Now coming to the first term. What is the first term? E raised to power ut. Wait a second. Or I'll directly say this one. E raised to power ut. I think something is wrong. So coming to this term, e raised to minus u, 1 minus e raised to minus t. E raised to minus u, 1 minus e raised to minus t. I know the value of e raised to minus t here. Can I substitute? 1 minus delta. Can I say?
Yes, ma'am.
So I can say that e raised to minus u, 1 minus e raised to minus t, the first term is equal to e raised to minus u delta. Now coming to the second one. What is ut 1 minus delta? Ut 1 minus delta. Can you tell me what will be its value? P is equal to log 1 over 1 minus delta. Can you tell how I came up with this basically? Or from ut 1 minus delta, how it is equal to this?
Ma'am, by reversing 1 by 1 minus delta, ma'am, we get minus sign, and ma'am, we can separate the powers.
Yes. So now I have both of the terms ut 1 minus delta as well as e raised to a minus u, 1 minus e raised to a minus t. So let's substitute those terms. Okay, e raised to power can I write it as e raised to a minus u delta by this? And can I write it as e raised to a minus u 1 minus delta log 1 minus delta, substituting both of the terms in that equation? Is it correct? Are you guys getting, or it's like going above the head?
No, ma'am, we are getting it.
Hmm. So just substituting both of the values there. I'll write it and then we'll come through it. Now can you explain how we come up with these steps? Wait a second, I think
Ma'am, in the previous term, shouldn't we, ma'am, take,
this is actually this is the step.
ma'am, we can take, ma'am, mu 1 minus del to the, ma'am, in the power of 1 minus del inside log, and then can substitute, ma'am.
Can I say they'll be cancelled? This is e and this is log 1 minus delta. This and this will cancel and this will come 1 minus delta here, and it will be in the power. Are you getting? What is the value of this? Simply,
1 minus del.
that is what we have done here. See, e raised to power log 1 minus del, 1 minus del, and it is in the power. Is it correct?
Ma'am, it is correct, ma'am, but ma'am, we should, ma'am, do one more step. That is, ma'am, mu into 1 minus del, ma'am, we should, ma'am, take it to the power of 1 minus del inside log.
Okay, what you are saying? Okay, we have this e raised to a minus mu del. Now, can you tell me the second step?
Ma'am, take mu 1 minus del, ma'am, term as power of 1 minus del inside the log.
Okay. You are saying this one as power of this.
Yes, ma'am. And then we can cancel, ma'am, e and log.
How can you take this as power of this?
And by properties of log, ma'am, power can be separated.
Are you referring to this?
Yes, ma'am.
A log B can, yes, absolutely correct. A log B, I was actually going directly only. Yes, A log B, we can write it as log B power A. That is what, thanks for this step. So that is what log A log B, A, this is constant log B. So log B power A, and E and log are cancelled out, and we have this. Now, how I came to this step?
I'm taking mu common and
Hmm.
I'm inversing that other term.
Hmm. 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 So can I say this? Can I simply say that it is less than exponential minus delta square by 2? And we came up with this result. Was this derivation very much exhaustive, or was it fine to understand? Should we go through it again once more so that the doubts which we are having should be cleared? Or you got this? Yes? Yes, come on. You got it?
Yes, ma'am.
Uh, I'll just go through, I'll have a quick revision so that others can also. So, what we have done, we have come up with the Chernoff inequality, that the sum is basically less than the expectation, and it is basically upper bounded by exponential decay. I'm referring this expected as basically as mu, basically, and I can say that it is equal to NP, basically. So, S is less than 1 minus delta mu, I have to calculate. I took the exponential on both of the side and did it e power minus t. When I'm doing this, basically the signs are getting changed. T is basically any parameter which is greater than 0, and this is natural log. We know that. Now, we have done the Markov inequality that x is greater than some constant. It is bounded by expectation of x over a. Similarly, we applied this Markov inequality to this. E raised to a minus ts is less than e raised to a minus t1 minus delta mu is less than expectation of x was this, over a was this. And we know that when we are multiplying, the powers get added up, or when the powers are getting added up, we basically do the product. And now coming to this term, expectation of e raised to minus ts, basically. What is s? S is basically sum of x1, x2 till xn. Now, I can write it as a product term by separating them. That is what I have done. E raised to minus t, x size and x are identical. So taking the power n, and now coming to, they are Bernoulli in nature, which means either they have with p probability they'll be successful, with 1 minus p it will be failure, basically 1 or 0, basically. Then I took p e raised to minus t plus 1 minus p 1. We took I have written this 1 minus p plus p raised to a minus t, taken p as common here and written like this. We have the property that 1 minus epsilon is less than equal to e raised to a minus epsilon by Taylor's theorem. So 1 minus epsilon, this is suppose epsilon, is less than equal to e raised to a minus epsilon. So I substitute the value here. Now I got this. If e raised to minus ts is less than equal to this, I can substitute here, basically. I substituted the value of this exponential here, and I also, NP is basically replaced with mu. So e raised to minus mu 1 minus e raised to minus t, this was already with us. And when we have the division, the powers get subtracted, so we got this was already minus, so added up here. And then we are doing the differentiation so that we can get the minimum upper bound, basically the lowest upper bound. So we did differentiation with respect to t. And then one more thing, so we got that t is equal to log 1 minus delta. And actually t, it shouldn't be let, basically we got the t is equal to log 1 minus delta. So, and then we substitute the values of this t is equal to log 1 minus delta here in our formula, in this formula, basically. So we took this. So before taking this, for the simplification, we only did e raised to a minus t, that was 1 minus delta, and then we put e raised to minus mu 1 minus e raised to minus t. E raised to minus t we have computed already, 1 minus delta, so e raised to minus mu delta. And then e raised to minus t minus 1, sorry, ut1 minus delta. Then we took t again, log 1 minus delta, we substituted, and we came up with this formula. Ut log 1 minus delta and e raised to minus u, we came up with this. We substitute the values of both of them in this formula, basically, this one. We substituted the values. And then e raised to minus, and then basically we went from log a log b is equal to log b power a, that we have written here. And then e and log got cancelled out, and we got this term basically, and we are saying that it is less than this. And this is how we prove this Chernoff inequality. Any doubts?
No, ma'am.
It took a lot of time, actually, 45 minutes just to, I think it was exhaustive. So we came up with many small things which were used, like Taylor series or the exponentials and the properties of exponential. So basically, if I say that bottom line or the summary of this is that summation is far away from the expectation and it is exponentially decaying, if I say that. I'll not go through much detail, just for the k-wise independence. So k-wise, I think we should move forward rather than or go through this. That is what I'm thinking. Okay. Let us go then. Let xi given I belongs to n, call it k-wise independent. If for all xi belongs to R, all j belongs to n with cardinality of j less than k, can someone explain what is this? What do you mean by first of all independent? And what I have written here? Yes. Come on.
Events are independent.
Yes.
Ma'am, K independent.
Hmm.
Ma'am, K events are independent to each other.
Yes. K. What about this formula? What is the relevance of this formula?
Ma'am, probability of number of events occurring together is multiplication. Ma'am, is nothing but multiplication
Yes.
of all those individually.
Yes. Why we are only doing the multiplication? Because they're independent. Can I say when they are independent, we can directly multiply them? And it should be equal.
Yes.
Basically, the intersection should be equal. That we have actually learned in previous classes, that P in intersection B is equal to PA into PB. Is this
Yes,
the basic from that only, I can say? If k is equal to 2, we can say that they are pairwise independent. If k is equal to n, I can say they are basically mutually independent, as we have discussed earlier also. Now, if I say about the independent events,
Ma'am,
yes.
ma'am,
Mm-hmm.
ma'am, can we say that it is, ma'am, extension of conditional probability about that
Yes, yes,
independent
yes,
event?
yes. It is actually the extension of the conditional probability. You're absolutely correct here. That is what they're trying to say here, which I missed. So I'm thinking that whether we should go through the probability boosting, or I should. Okay, I should move forward as we are already behind some lectures. If I say, okay, let us take intuition behind that. If I say that I toss a coin n times, or I think, okay, that is leave this, we'll go. This is just only that it can be linear decay also, it can be exponential decay also in the Chernoff bound. If I'm if delta value is logarithmically logarithmically away from them, then we can go through the linear decay, or it can be exponential decay if delta is suppose half. That is what the examples are shown here. And then we are I'll just give you the overview of this, I'll not go in detail about probability boosting. Can someone tell me what is probability boosting? Any idea? Yes, come on.
Ma'am, similar to weak law of large numbers, ma'am, in that case, ma'am, that was linear. Ma'am, we were increasing, ma'am, ma'am, our chances of succeeding by linear terms. But in this case,
Hmm.
ma'am, it is exponential. That's why it is more useful in CSS
Hmm.
application.
Yes, we can say that what we were doing in we I already discussed initially, like what we are doing in weak law of large numbers, that we are repeating basically the experiment uh, n number of times basically. So we are doing the same here also. Is it correct?
Yes, ma'am.
And then what we are doing is, we are suppose what they are doing is, we are output, we are making the output is a majority vote. What do you mean by this majority vote? Like suppose I'm designing a new algorithm, and I'm repeating the algorithm this huge number of times, and the output is a majority vote. What do you mean by this?
Uh, Ma'am, the algorithm gives only two values, that is true or false. Ma'am,
Mm-hmm.
if we, do the test and odd times, ma'am,
Mm-hmm.
ma'am, it is necessarily, ma'am, it is bounded to be, ma'am, that one thing is majority in its majority and in other is not.
Can you repeat like what you said, that okay, we are repeating it n times, then
Ma'am, if we take m odd,
hmm. Hmm.
ma'am, ma'am, then ma'am, we will get absolute majority, ma'am. There will not be any tie or something, ma'am. And
Uh-huh.
we can
Yes,
output
yes.
the majority vote, ma'am. That is, either 1 or 0, like that.
So can I say that majority should be the right answer,
Yes, ma'am.
and it will be wrong, our assumption and every algorithm will be wrong only if the majority is the wrong answer?
Yes, ma'am.
So basically, as he told that weak law of large numbers, it's similar to this, but it is exponential in nature. That's why it is very much useful algorithm in like a randomized, useful in randomized algorithm, where we are having the randomness in our studies. So there we are using it. Now coming to stochastic process. I'm missing some things. I think you can cover them because and if you have any doubt which I am missing, like only the union, factorial, or Stirling's estimate we have used there. So if you have any doubt, we can discuss that. Can I say stochastic process is a sequence of random experiments that may depend on previous outcome. First of all, before starting with this stochastic experiment, let's first, can you tell me what does stochastic means? What is the meaning of stochastic itself? Rather than going in detail about stochastic process or something, what is the meaning of stochastic? What do you think by the definition itself? Come on. Can I say randomness? Whenever we have the randomness, random, the system which is having random there, that is basically stochastic process. Whenever I'm using the word randomness, stochastic actually means randomness there. So what do you think? What can be the randomness in the experiments which we do in computer science or in our real lives? What can be the randomness? Yes. Yes, yes. What are random experiments? Example? Come on. Is coin tossing a random experiment? Stock market or random process, stock price and all? Am I
Yes.
audible? Hmm. So basically sequence of random experiments that may depend on previous outcomes, or the other definition which is given, that stochastic process is sequence xt, t belongs to I, of random variable taking values in state spaces. We use the state space, action space, transition probability usually in our Markov chain. So I'll tell you. Can someone tell me what is state space, or what is the can someone tell me what is this definition, the gist of this definition? Yes.
Uh, ma'am, ma'am, can we say that ma'am state space is nothing but sample space? Sample space.
Yes. State space is nothing but
Ma'am, sample space.
sample space. Yes, in one sense we can say that. Okay, I'll go forward and then we'll study about it more. Yes, we can say that it's sample space as well. Okay, in RL context, okay, after this lecture will over, I'll tell you how in the Markov chain, how the state space, random space, action space, randomness, transition probabilities, and all play the role there. It plays a huge role in RL also, reinforcement learning also. So basically, we have some states, we take some actions. Okay, I'll first introduce Markov chain, then we'll come up with this. So it can be discrete as well as it can be continuous. Like as you told, okay, let's for now consider it as sample space only. Now coming to this. So what I have written, can someone tell me what is this? Conditional probabilities intersection. What do you mean by this? This equation? Yes, come on.
Dependence of events on one another.
Yes. So can I say that
In a
x1
series.
when I'm doing x2, it will depend the it will depend on the output of x1 basically. When I'll do x3, it will depend on x1 and x2. I can say when I'll do x4, it will depend on x1, x2, x3. The previous events, the current event is depending on the previous events. So what do you mean by this statement? Order is fixed. As in class, they have told order is fixed. What do you mean by this?
When events are occurring in a fixed order,
Why?
because one is dependent on another, and if first doesn't occur, then doesn't
Hmm.
second can't occur.
Yes. So if I say that third is occurring first and first is occurring last, after the third, it cannot occur because third is dependent on first or and second. Fourth is dependent on first, second, and third. So first should occur, then only third can occur because it's the current input is dependent on the previous outputs there. I can say in the layman words. And if I say about independent, is it simple that if they are independent, then we can simply multiply them because they are independent? Here, nothing we can say of the order and all. Is it fine? Now coming to the
Yes, ma'am.
Markov chain. Hmm. So Markov chain basically is a stochastic process where this is the main gist and very important basically in the computer science itself, the Markov chain. Can someone tell me what do you mean by this? What is this Markov chain? What I have written here? It's very, very important topic, which is taken from probability, applied in networks, computer networks, applied in reinforcement learning. So yes, can someone tell me?
Ma'am, probability of a event occurring is dependent only on the previous one.
Yes, absolutely correct. So current state depends on only the previous state, not the whole history. Can I say this? It is not depending on the whole history. X4 is only dependent on X3. X3 is only dependent on X2. X2 is only dependent on X1. X4 is not dependent on X2. I can say, if I say that X4 don't depend on X2, X1 x1 or so on. It only depends on basically x3 here. The current state depends on only the previous state and not the whole history. That is basically the Markov chain or Markov process. Now coming to independent events, the tossing of the coin basically. If I say toss the coin many times, let xi be the number of heads till ith toss. Then I'll write it and then we'll go through it. Xi is equal to xi given xi minus 1 is equal to xi minus 1 intersection, so on. Xi is equal to xi. I'll write it and then one of you can explain this. Now, can someone explain me? We have done what is basically the Markov chain, which is dependent on only the last state, previous state, not on whole history that we studied. Now, what about this example? I have written it. Please, can someone of one of you explain this? Yes, come on.
Ma'am, may I?
Hmm.
Ma'am, if we suppose, ma'am, in number of heads till current process is x, ma'am, and, and in the next state, ma'am, we are tossing a coin again. Then we can then the probability of getting a head again is half, if it is say a coin. If then the difference is half. I mean, sorry, the probability is half. Uh, then that means in current and in the next state, the difference is equal to 1, then its probability is half. Otherwise, if we take difference more than 1, like 2 or 3, it is not possible because we are tossing only one coin.
So basically, can I say one more thing, that if you're tossing a coin, it is not dependent on previous state, then how we are saying that this is Markov process? You said, okay, I'm tossing a coin. It is either head or it is either tail basically. So probability is 1/2. So how you are saying that, okay, I tossed the coin one time, I got it head. So if I toss the coin next time, will it depend on what I got the last time? First
Yes.
question. I tossed the coin, I got head. Second time, will it depend on the state that, okay, last time I got head, so I should get head or should I get tail? Is it dependent on the previous state? Yes or no?
Yes, ma'am.
No, ma'am.
Yes, ma'am.
Okay, one of you are saying, one of you is saying yes, one of you is saying no. Please, can you explain both of you? Come on.
Ma'am, if we want five, ma'am, suppose if we want 5 heads in our and we want to 5 heads, then we must get 4 heads in the previous
You are
in the
correct.
previous.
You are correct. I think he
That's
said no,
why.
because what I'm asking, I'm not asking now of count. You are saying of count. If I say normally head and tail, maybe he said no, because I was asking normally head and tail, it doesn't depend on the previous state. Am I correct now? No
Yes, ma'am.
counting. No. Yes. What about other? normal count. Now if I go about counting, then you are correct that yes, if I'm saying that, like suppose the last time the number of heads was 4 and I want the number of head as 5, I should know what was the previous state, that it was 4, now it is 5 basically, so previous state is required. Both the things are correct now.
Yes,
Yes,
Hmm.
ma'am.
Yes. So yes, why it should be maximum 1? You were telling something, why it should be like less than equal to 1, why not otherwise 2 or something? Can it be 2, can it be 3 or something?
no, ma'am. At
How?
max we can get only one head. At max we can get
At
only
my,
one head.
yes. So can you explain why it is 0 and why it is okay, 1 by 2 is fine, we can get okay, and else it is 0? Yes, absolutely correct. And now we also call it as homogeneous. Any idea why we call it as homogeneous? What do you mean by Markov chain being homogeneous?
Because it is independent of time.
Wait a second. I think my independent of time. Can you give example?
If we consider the same example, number of heads, then
Hmm.
it is same as in case of getting 5 heads as in 7, 9, etc.
Hmm. So can I say it is basically independent of time, basically? So let's move forward. So before moving, okay, or either we'll go through this.
Ma'am, your slide is not visiting.
Wait a second. Is it visible? Like now
Yes,
it's
ma'am.
fine. Hmm. So now we went through like how the independent random variable basically it can form the Markov chain as well. The sum of them basically. If I say the sum here, we saw with the example that how they are forming the sum is basically the Markov chain. What do you mean by IID? Can you give the example?
Independent and identically distributed.
What do you mean by independent and independent? Okay, we discussed a lot. What do you mean by identical distribution?
Same distribution is used like
Yes.
like binomial or something.
So the same distribution we are like undergoing every time, that is basically in a identical in distribution, and independent means one event is independent of the other event. So basically they form, when they are IID, they form a homogeneous Markov chain. Now coming to the Markov chain. Okay, so rather than going through this, let us take an example. Maybe it's not it's out of scope, but still just to give an intuition how Markov chain is helpful and so. So maybe it's MDP or Markov decision process. Okay, let's go. So basically, I have the state, suppose um, I have this clients, IoT devices. And I have this server basically. And my main goal is to reduce the cost while communication. I want to communicate the data to the server from the IoT devices and to reduce the cost while communication. Now, this cost can be, suppose it can be uh, the reduction of time, or I can say, just I'm giving you the intuition how the Markov chain basically is built, and basically how we use this Markov chain in RL, Markov decision process, how we take this decision process. Though it's out of scope, but just to give the intuition behind it. Suppose now I have this, I want to energy or battery, and basically time should, and they are vice versa. If I increase the time, then if I decrease the time, energy is basically increased, and energy, if I decrease, then time is basically decreased. Then at this case, we usually use that Markov process because it's sequential. I transfer the data, then the data will come from this server, then I'll transfer, suppose they are aggregating the data of everyone, and uh, aggregating and averaging them and sending it back, suppose. So I'm sending it with the state space, I can say, suppose, or I'll, for the ease, I'll take only the reduction of battery itself, reduction of energy. So basically this is a sequential process, I can say, going, coming. This process goes on repeating until, suppose, this is ML is taking place here, and until we are getting some convergence state, like in good amount of accuracy in the model. Suppose the model is transferred or data is transferred to the server. So suppose, what do you think, what can be the state space? Can I say the batteries here, the battery 1, battery 2, battery 3, or so on, batteries are the state space. I have to take a particular action. I have to transmit the data with some transmission power, or with some transmission power, that my battery should be utilized less. There should be action taken. This is basically, I'm going beyond the scope, but still let's have this intuition. And if I say randomness, if I'm communicating, maybe the bandwidth is fluctuating, so bandwidth is random here. And what action is basically, these are and the transition probabilities are also given to me. So basically I'll have the Markov chain also here, or from this battery I'm going to this, this, from this to this, with this probability, with this probability, and this is basically MTP. Okay, I shouldn't go in that much depth. If you want to go through this, basically I have taught RL also in NPTEL. You can go through these MTP videos also, or if you want to discuss, we can discuss some other class. So this is how the sequential process, just the main gist or intuition of this, the sequential process, how it takes place, and how the randomness is induced, how it can be helpful in computer science, or in our experiments, or in our research, I can say. So basically the whole Markov chain is built up here. That is what the main intuition behind this. And the Markov chain can also be useful in other aspects also, like here it is useful, like with what battery you are what is the state space, how much battery is left after transmitting, after taking an action with P1 transmission. Like suppose, what is this probability with P1 transmission power 1 by 2 times I'm sending, other 1 by 4 times I'm sending, with transmission power 3 I'm sending 1 by 4 times, or sorry, 3, something like that only. So basically then which transmission power I should take, so that my time should also be reduced, at the same time battery should also be reduced. That should be the best action. And the randomness is induced, that is why it is a stochastic process, I can say. Something you got? or it's going above the head? Yes. Okay, I shouldn't go in that much depth. Some I just want to give you that how this can be used in various applications basically. That was the main idea behind this, how the Markov chain basically, if I'm going from A to B with some probability, with some action, or I'll take only probability, then I'll go to C. This is the state, this is the state, this is the state. Now Markov chain, it will depend only on the previous states, we know. Is it clear? Yes. Am I
Yes.
audible? Okay, what is the course name? Reinforcement learning. Basically, last year or last year only I have taught this. So you can go through this, and it's exhaustive course because it's RL there. So these are the basics which I use there, the stochastic process and all. And then we came up with we also come up with the transition probabilities, like what should be the probability of going from A to B, A to A, A to B, A to C, and this columns and rows should add up to 1. This is the property of the stochastic matrix. We'll continue this, the drunkard walk or this Markov chain in more detail in the next lecture. Let's go through once the assignments, the assignment 2 and assignment 3. I'll just come and have water. I'll just come in 5 minutes. So we'll meet in 6:25 and we'll try to solve the assignments together. Is it fine?
Yes.
Am I audible?
Yes, ma'am.
So let's go through those assignment problems. Let's start with the week 4 itself, because week 5 is submitted or is yet to submit? I think yet to.
Yes, ma'am. Yet to.
Okay. I think week 5 is all about Markov chain and all, no? Transition
Yes, ma'am.
probabilities and Markov chain. Okay, let's go through week 4 assignment. Suppose Google Drive has file X. I want that you should answer this, because you all have already done this. So suppose, okay, I'll write it in short, basically. Google Drive has file X of length L, and the version of file on user's computer is Y of length L. Google want to decide whether they need to update the version of file. To do this, they use equality check protocol covered in class. So equality check, you are clear, or you need the further revision about equality check? Is it clear? Like, we are only sending the residue and the prime numbers, and then we are checking it rather than
Clear.
sending the whole file. So Google will update the file if and only if the protocol says X is not equal to Y. So if the two files are not equal, then only the Google updates. So now consider the two scenarios. If the two files are equal, the Google will never update the file. If the two files are different, then Google will not update the file with probability less than 1 by n. So what are your views about this? Which one is true? You also can open your assignments on your systems. First one is true. If the two files are equal, then Google will never update the file.
Yes, ma'am. True.
What about the second one? Why it's true? If it is true, then why? Is it true?
Yes, ma'am. It's true.
Can I say that if two files are different, Google will not update the file? Google will not update the file with probability less than 1 by n. What do you mean by this statement? That 1 by n is very less, I can say, which means that Google will update the file if they are different. Am I making sense by saying this? Yes, come on. Come on. Should we proceed forward? I can repeat it, or we can go through it again if any doubts are there.
No, ma'am. It's clear, ma'am.
So the next question: the Yamuna River experiences overflow flood once in every 100 years. Assume that number of flood is modeled by Poisson distribution. Can you tell me the formula of Poisson distribution?
Lambda to the power k upon k factorial into e to the power minus lambda.
Yes, absolutely correct. Now, what is the value of lambda? Can I say 1? 1 over,
1
can
over
I say
100.
1 over 100 or 1?
Ma'am, 1.
How 1? Because it is rate of the change, I
Ma'am,
can say rate 1 in 100 years. Can I substitute the value? So probability of x equal to 1. The same as the probability that there will be no overflow in next 100 years. Now coming to no overflow. No overflow means probability of x is equal to 0. Are they same?
Yes, I'm seeing.
Hmm. So can I say that A is the option, the same as the probability if we are having 1 in 100 years or no overflow flood in the 100 years, they are same only. Is it correct? Should we proceed?
Yes, ma'am.
Third question, what do you think about this? Can someone read and also answer it? Can you open your assignments and read it?
Yes, ma'am.
Mm-hmm.
Ma'am, let x1, x2 up to xn be binary IIDs,
Mm-hmm.
random variables.
Mm-hmm.
Then consider S is equal to sum of all those such that expectation of S is 3, then which of the following is true? And first statement is that probability of S lesser than 1 is lesser than e raised to minus 1 by 3, and probability of S greater than equal to 9 is lesser than equal to 1 by 3.
So what will be the formula used in first one? Any idea? Can I say Chernoff bound?
Yes, ma'am, my first one is simple.
And what about second? I have also not seen actually.
In second one, I have doubt on.
Okay, I have also not seen this question. Maybe in the next class, or what about the other student? You have seen this to solve it. Maybe in the next class, remind me of this. I'll go through this question basically. Or okay, remind me this question. I'll solve it and go through it because they were all like this only. Maybe I have to solve this. The first one is Chernoff bound. It's fine. What is the second? Is it Markov?
Markov
No, ma'am,
inequality.
Markov
ma'am,
inequality. Hmm? So can you tell me
ma'am,
about
can you
Markov? Yes.
uh,
Any
Probability of x greater than equal to a is less than equal to expectation of a upon a. Expectation of x upon a.
hmm. Any doubts now?
No, ma'am.
What about other student?
yes, ma'am. Ma'am, it was simple. Ma'am, I was
Uh,
doing mistake with.
hmm. I thought that okay, you should once see. Okay. Now, what about fourth question? Can you read and solve?
Ma'am, can you once do the first one? I think it is incorrect
Okay.
because
I have not
I
done
have
this. Mhm. Okay, first, can you tell me the Chernoff bound the formula? Yes. What is the value of delta?
now 2 by 3.
Okay. Now coming to this e raised to power. Expected x is expectation of x is -3. Delta square is 2 by 3. That is 4 by 9. So what is its value?
It is 2 by 3, I guess. It is e to the power minus 2 by 3. But ma'am, it is saying,
It is saying that first one is true.
yes, ma'am.
Okay. Maybe I'll go through. It's actually 2 by 3 only. Maybe it's an error basically. It's 2 by 3 only.
Okay, ma'am.
Now coming to the next question. It's simple only. How it's equal to variance of x minus we know that variance of x I can write like this and 3 square variance of y. Is it correct?
Yes.
Basically a square. Whenever we write variance of ax is equal to a square variance of x. Is it correct?
Yes, ma'am.
Yes, ma'am.
Now coming to the fifth question. Let x1, x2 till xn be IID random variable with mean mu. Let sum is equal to x1 till xn. Define a new random variable w is equal to x1 over s plus 1. What random variable nw converts to? Okay. Yes, any idea about this? Okay, n, can I say nx1? Maybe I have also not solved it. Let's see. nx1, okay, and what they have given n w as n tends to infinity is, can I say that
We can take n in.
can I take this? If n tends to infinity, my sum by n basically is approximately equal to mu by
Yes.
large numbers, and s tends to n mu. Now I can write it as n mu plus 1. Or if n is very
We can divide
large.
it.
Uh, so basically x1 by mu. Is it correct? Is it fine?
Yes, ma'am.
Now let's see. I think we haven't solved the assignment 3 also. Let's see the assignment 3 also. So Alice and Bob eat 1 and 6 apples with equal probability. Between 1 and 6 apples, that is for k belongs to 1, 2, 3, 4, 5, 6. Alice, Bob eat k apples with probability 1 by 6. What is the expected value? Yes. Should be solved. Yes, come on. Expected value. Can I write like this? Expected value of the total number of apples they eat.
Yes.
So for both of them, it's 7. Is it correct?
Yes, ma'am.
Yes, ma'am.
Now, can someone solve second question and share the screen? Or I'll solve it. Like you have solved this question, or you were having the doubt in this? Yes. Have you solved it, or there was a doubt in this question?
Ma'am, I solved it, but I don't remember, ma'am. I need to look it back.
Okay. So Eve has found a time traveling machine and wants to go to some year in past. She picks a year from the set 1 to till 2024. Okay. The probability that she picks a year P is directly proportional to P with the same probability constant beta. P of year is equal to P is equal to beta P. What is the expected value of the year that she picks up? Can I say this is equal to beta P? And I can say that the probability is equal to 1 here.
Ma'am,
Taking beta
summation of beta
constant.
p square.
Summation of beta P square. Yes, I'll come to that. I'll come to that. Don't worry. Beta P square. I'll come. Beta P square. Yes. First of all, I'm only calculating for P is equal to year P. Then I'll come to P multiplied by P year. That will be equal to beta P square only. Now I'm only calculating for this. Got it?
Yes, ma'am.
So what is this? What is the formula of like a sum of n natural numbers?
Ma'am, n times n plus 1 divided by 2.
N into n plus 1 divided by 2. So I can write it as beta 2024 multiplied by 2025 divided by 2 is equal to 1.
Yes.
Or I can say beta is equal to 2 over 2024 multiplied by 2025. Now, as you said, expectation of this year, that is equal to summation of P is equal to 1 to 2024, P into probability of year is equal to P. That is equal to beta P square, as you said. Beta can take it outside and then know the value. Now, what is the sum of n square natural numbers?
Ma'am, n times n plus 1 times 2n plus 1 divided by 6.
So similarly, I can write it as what is 2n plus 1?
Ma'am, 4049.
4049 divided by 6. So whatever will be the answer, it should be equal to this. I hope so. 2024, they'll be cancelled up. Can you calculate 2 into 4049 multiplied by 6? Are we getting the right? Or 4049 divided by 3? 1's 3, 3 is 9. Are we getting incorrect or
Ma'am, it should be 1349.
it should be 1349, but it is not coming as 1349, no?
No, ma'am. No.
It is 1349.67.
So what is our answer coming here?
Ma'am, it is same.
Same? Okay. So now coming to the next question, let x be random variable that takes values 1 or 2 with equal probability. Okay. X 1 or 2 basically, and y is a random variable that takes an integer value 1, x plus 1 with equal probability. Okay, what is expectation of xy? So let us take first x is equal to 1. Now, let us not talk about xy, let us only talk about y here. So what is the expected value of y given x? Can you tell me? If x case 1, x is equal to 1. Yes, come on. I'll write it and then can you explain? Yes. Can you explain this? Come on. Come on, come on. Am I audible?
Yes, ma'am.
You have doubt in this? You can say, I'll explain it. What does expectation mean only? So if I take the value 1, what should be the y value? Either it should be 1 or either it should be 2. So what should be the mean? 1 plus 2 by 2. Am I correct by saying this?
Yes, ma'am.
Now coming to xy. I know that value of x is equal to 1. So simple. Now coming to case 2 when x is equal to 2. Now can you tell me what should be this value of y? What can y take the values? Like here it can take 1 and 2 in the first case. What can it can take the values here? And what
Ma'am,
should
1,
be the
2, and 3.
1, 2 and 3? Now simply calculating the expectation of xy. What is the value of x is equal to 1? 1 by 2 because half of probability. What is this? 2.
1.6.
It's okay. 1.5, sorry. 1 by 2. And what is its value? 4. What is the answer? It's 11 by 4. Are they equal?
Yes, ma'am.
Any doubts in this question? I have to go
No, ma'am.
somewhere. Maybe we'll end up the class. The other two questions, are there any doubts?
No,
Or
ma'am.
maybe we'll, okay, they are clear. They are maybe theoretical only, not that much. So you are attending the like Friday's lecture also or only this Saturday?
Only this Saturday.
Okay, okay. And what about the other person? Okay. Okay, then. Thank you, class. So
Thank you, ma'am.
maybe we'll proceed with the next part what, where we have left. That is the more of Markov process and all, Markov chain and all in the next lecture. So thank you.